Good morning for this second press conference on polar ozone, and I would like to introduce to you Geir Braten from the World Meteorological Organization in Geneva, I think.
Okay, fine.
That's right.
Good morning, everybody. Today we are here to speak about Arctic ozone loss, and today WMO is publishing a press release. It has just been released now. It's off the embargo as we speak now. So what we have seen this winter is that ozone loss in the Arctic, as caused by CFCs and halons, so man-made substances, has reached like an unprecedented level. So I'm supported by some colleagues here. Marcus Rex from the Alfred Wegener Institute in Germany, Farah Khosravi from the Stockholm University, Florence Gauthier from CNRS, and in the audience we also have some other experts. I can start in the back row with Frode Stordal, who is a modeler. He has actually worked on Arctic ozone loss since 1988, when the Americans had a campaign out of Stavanger. Then we have Sophie Godin-Beckmann, Lamont Poole is here, Mark von Hobe, and Michael Pitts. And I think I have included everybody now who is like and you're Martin Sinhuber. He is pretending to be a journalist.
Jean-Pierre.
And Jean-Pierre Pomerot standing in the back. So if there are difficult questions, we will have lots of people to help answering. I'll just give a very short introduction, why we have the ozone layer, what it's about, and then Farah will speak a bit about how ozone is depleted, the mechanism behind ozone depletion. And Florence will say something about her measurements and technique to quantify ozone loss. And then Marcus will show us something that he has done with a different technique. So first let's look at the ozone layer. So this plot here that you see now, it shows the distribution of ozone in the atmosphere. I guess most of you already know this, but just to make sure that we know what we're talking about. We have some ozone in the troposphere down here. It's quite small amounts, but the ozone layer starts up here about. This where it starts can vary from 10 to 20 kilometers actually, but around 20-25 kilometers we have a maximum ozone. So this is the stratosphere, and this part here, this is what we call the ozone layer. And this is what protects us against UV from the sun. We also have a problem about ozone in the troposphere, especially close to the ground, what we call the, let's say, surface ozone or tropospheric ozone. This is a pollutant because ozone is a corrosive gas, so we don't want to breathe it. But we want as much ozone as possible up in these layers to protect us against UV from the sun. So this is a picture to show that long-wave UV that we call UVA is not absorbed so much, so it actually goes through the ozone layer and hits the ground. But short-wave UV, UVB, that is actually causing sunburn, is to a large extent attenuated or absorbed by the ozone layer. If we had no ozone layer, we would have 70 times more intense UV than we have actually. So you can say that the ozone layer constitutes like a sun cream with factor 70, to put it simply. So that's why the ozone layer is important to us, and that's why we are concerned about ozone loss. Also, what I want to point out is that the ozone loss that we have seen now in 2011 in the Arctic it's not because the Montreal Protocol does not work, because the Montreal Protocol actually does work. And here we see some curves of what is called EESC. It is just like a surrogate for a combination of chlorine and bromine. You take all these ozone-depleting gases and combine them, and we call this equivalent effective stratospheric chlorine. And the black curve on the left here, this shows what would have happened if there had been no Montreal Protocol. If the use, the production and consumption of these compounds had just continued unabated, we would have got a curve like this. It would just go straight up. And then we had the Montreal Protocol in 1987. This whole process with the Montreal Protocol was sped up because of the discovery of the ozone hole in 1985. And but we see that the first Montreal Protocol, it would help a bit, but it will actually not help in the long run. And then a few years later in London, these delegates met again and made this Montreal Protocol more strict, but still it would also, in the long run, just go straight up like that. It was not until 1992 in Copenhagen that the parties of the Montreal Protocol were able to agree on strict enough measures to really bend this curve over and get them good effect in the long run. And then later it has been strengthened on several occasions, like in Beijing, and also in 2007 in Montreal again, 20 years after the first agreement. And we see that it will actually come down back to close to, or at least back to the natural level. But it will take time. So the next figure shows in more detail for mid-latitudes in the red here and the polar stratosphere. And it shows that it came up like this, and then it's now on the way down again because these compounds are no longer consumed or produced. But we see also that by 2008 we have only made 10% of the way back to the natural level, which are called 1980 levels. This is like the benchmark year. Before 1980 there was no ozone hole in Antarctica and also not in the Arctic, so we used 1980 as the benchmark year. And by late 2008 we have only made 10% of the way back to the natural level, or pre-1980 level. So this shows that these compounds, they have a long lifetime in the atmosphere, and there is nothing the Montreal Protocol can do about that. We can just ban and stop the consumption of these compounds, but what has been emitted will still float around for decades to come. But this will come down slowly. So, and then what actually decides how much ozone loss you will get, so this applies both to Antarctica and to the Arctic, is how cold the winter gets. This is now a plot showing recent Arctic winters in the stratosphere. You average the temperature, you take the minimum temperature measured anywhere between 50 and 90 degrees north. So this is the polar cap, if you wish. At 50 hectopascal, this is like 18 kilometers up in the atmosphere. And we see in red here, this is 2011. I made an error there, so it should be 2011, just point that out. And we see that this winter has been maybe not colder than anything we have seen before, but the point is that it's cold also late into the spring. And this we will hear more about, why this is important and why this causes ozone loss. So, it's the combination of still fairly large amounts of chlorine and bromine in the atmosphere and low temperatures. And what we will see is that the ozone loss this year is what we call unprecedented. We haven't seen such a degree of ozone loss before in the Arctic, but it is not unexpected. The scientists have already many years ago predicted or forecast that in the case of a cold winter, we will see massive ozone loss. This is my last figure, so by that I leave the floor to Farah, who will show, yeah, you have it actually here.
Yeah.
Then we'll pick it up. It's this one, I think.
Yes.
Yes.
Okay.
And then let's say F5, and then okay.
Mm-hmm. Okay, now I will explain what are polar stratospheric clouds and how do they destroy ozone. One thing you didn't mention so explicitly is we need cold temperatures, the chlorine and the polar stratospheric clouds to really get ozone destruction. And I want to start with some pictures showing these clouds. So they form high up in the atmosphere, at around 20 kilometers, so between 18 and 25 usually. And they look very special. They have very colorful. They look very colorful. They're also called mother of pearl clouds because they have these nice colors, and it's how they reflect the light. And since they're so high, the sun is shining from below. Because you have to know that they are formed. The name already says that they are formed in the polar regions and high up in the stratosphere. And and they're below. So usually the sun is very low, low about the horizon. And so I have different pictures. So this shows more large PSC or polar stratospheric clouds, and here's only one small one. So they can have different extensions in the horizontal. So there can be very large areas of polar stratospheric clouds, but it can also be only one single cloud. And these are typical pictures taken in Kiruna. That's a place in northern Sweden where usually these clouds can be very well observed. And as I mentioned already, so they form between 15 and 25 kilometers. They need very cold temperatures to be formed, so it's from minus 78 degrees Celsius. They can extend in the horizontal from 10 to 1,000 kilometers, and they form above the polar regions in winter and spring. Thanks. And yeah, that's a figure showing that's relating to this winter, showing the area of polar stratospheric clouds for several winters from 2003, 2004 up to the latest one. And the latest one is where's the mouse? The red curve here, the thick red curve. And what's special here is, in general, the area of the polar stratospheric clouds wasn't that different from other years, but it extended much longer into March and April than it was the case in previous winters. And
actually, it's still going on. The rest of the curve of the prediction, there's a little bit at the end.
Yeah, that's true. It's still going on, so it's still up to until mid of April. And on the next figure, I have a comparison looking at the temperatures. Which one needs to form these clouds? The red curve is the Arctic, and the blue one is the Antarctic. And in the Antarctic, usually these formation temperatures are reached much earlier and extend over much longer time than they do when it's the case in the Arctic. In the Arctic, usually these low temperatures below minus 78 degrees are only reached for a certain short time period. And what was special this winter is, it's already what Gaia showed, is if you look now here on wet curves, showing the temperature versus the time, the months, and in red the previous winter, the winter we have now, and in blue the last year winter. And in the blue curve, you see the typical warmings we have in winter time. So usually mid-January, end of January, temperature started suddenly to decrease and get very warm, and then the PSC dissolve, and then the ozone destruction, all this season is over. But this winter it was like that, like here in the red curve, that the cold temperature extend very long and are still cold up to now. And with the green curves, they show the formation temperatures, and we have here two because there are liquid and solid particles, and usually first the formation temperature for the liquid particles reach, and then the one for the solid ones. And to show now how the ozone destruction actually is happening in connection to this cloud. So the first thing is, the first thing I have to explain here is we have again here the atmosphere regions, the lowest atmosphere region, and then the area where we have the polar stratospheric clouds. And the first thing which happens in winter, as soon as it's getting cold, the air masses start to sink down and further cooling, and then they isolate the air masses, and when the air masses are finally isolated, then we have the polar vortex. And then usually in that area temperatures get very cold and the air masses are isolated, and there's no mixing between the air outside of this vortex. And the first step which is happening is here on the left side, marked by a 1. Can't see the mouse. Yeah. So that is the formation of the polar stratospheric clouds. That's happening in the polar night. Then the second step also in the polar night is that some reactions occur on the surfaces of the clouds, and they form. So first of all, we get inactive chlorine species, but they start to form some reactive chlorine species. And as soon as the sunlight is coming back in the polar regions, ClO and Cl, so active chlorine, is released in another reaction cycle, and these in the end initiates then the reactions which destroy the ozone depletion, or cause the ozone depletion. Yeah, and I think that was. No, it wasn't my last slide. I had another one again showing the same one on the left side, the inreactive species, and then the reactions on the cloud leaving or releasing Cl2, and then the Cl2 can be transformed to atomic chlorine, and that atomic chlorine again in the end destroys ozone. Okay.
Okay.
Yes.
Do we want to have questions on the fly, or do we wait with questions until
whatever you prefer.
Yeah.
If you want to go on.
At the end.
At the end, okay.
At the end,
Yeah.
it's better.
So Florence, is it here?
Yes.
Yeah. Is it this one?
This one.
Yeah. There we go.
I need the mouse.
Just get it around back.
It's stuck here.
So I will try to answer all these questions. What happened this winter? Is this new? Is the reason understood, and is it similar to what we observe in the Antarctic? So here are some maps seen by satellites. On the left, it's YASI on METOP, and on the right, OMI on AURA. And both satellites show a low area with a low ozone columns at the end of March and at the end of April.
Beginning of April.
So what I'm doing is I'm measuring this ozone with a network of UV visible instruments from the ground and monitoring the ozone layer since 20 years. So here is a location of this station in the Arctic, 8 stations. And these stations are part of an international network, which is the NDAC, the Network for Detection of Atmospheric Composition Changes. And with these measurements of ozone, we compare with a model in which ozone has no reaction. So we call this a transport model. And by difference with the transport model and the measurements, we can determine if there is a loss, a chemical loss or not. So at the beginning of the winter, here in December, there is no loss. But at the end of December, beginning of January, we see some difference between the measurements and the model, reaching something like 10% at the end of January. And suddenly, in February and March, when there is sunlight, you see the measurements which has a large difference compared to the transport model, and we reach something like 40% of the column which has disappeared. So this is the value we reach at the end of March this winter. So this is, if we compare now to previous winter, usually during cold winter we observe something like 20-25%. Once we observed 30% of the column which has disappeared. And during the warm winter, we have something like -5 or -10%. But this winter was really a record one. We observed some preliminary results, of course, but 40% of the column has disappeared. This is also observed in the model, and here is results from a SLIMCAT model from UK, at a specific level, where he is modeling how much ozone with the same method, comparing to a transport model. And he is, on this curve, you have all years since 95. And this, in black, you have the results from this winter. And again, you see that this winter is really observing a larger loss than during any other winters. So he is monitoring something like locally at 17 kilometers, something like 70% of the ozone has disappeared. So the ozone mechanism has already been explained by Farah. So you need the polar night, the temperature decreases, you need PSC to form the chlorine species, and you need a well-isolated vortex. Sorry. And then second phase, the sun is back, and then the catalytic destruction can appear. And after phase 3, the temperature increases and the activation of the chlorine species and the ozone loss stops. So now we are in phase 2. The sun is back, and we observe ozone destruction, and it did not stop. So why? So you saw this curve already. So here you have the minimum temperature at around 17 kilometers. And again, you have the curve for each year since 94. And this 2011 is a cold winter, not colder than previous one, but long and persistent in March. So cold winter, persistent in March. And with temperature below 78, almost during the whole winter. Here is a comparison of what happens in the Arctic and Antarctic. So you have in red all minimum temperature at 18 kilometers since 95. And in blue, the same curve, but for the Antarctic, of course, shifted by 6 months. And you see that this winter, 2011, we are on the lower side of the Arctic, but we reach now some temperatures that are observed in the Antarctic. So what is the result for the column? So for the column, as I shown already, we are now observing something 40% loss, which is of course larger than we observed in the Antarctic, which is more about 50% of the column disappears in the Antarctic. But we are at the level of what we observed in the 90s, at the beginning of the 90s. So just to summarize, so this winter we observed 40% of loss for the column of ozone because we had a long-lasting cold stratospheric temperatures, a stable vortex, large areas with PSC, and a very fast destruction in March. And the vortex is still stable. And here you have a pictures of the vortex forecast for the 9th of April. And the vortex is still present, and we will see and follow what will happen in the next days. Thank you.
Yeah, then we can give the floor to Marcus.
And we should switch the computer here. I think you need to press button number 5.
Okay.
Yeah, that should work. We know that the ozone layer in the Arctic, particularly in the Arctic globally, but also particularly in the Arctic, is a very variable thing. So deficiencies up there in the Arctic ozone layer can be caused by natural dynamical transport processes, and that has always been the case. And nowadays, since mankind has released these CFCs, deficiencies can also be caused by anthropogenic chemistry. So once we find a deficiency in the ozone layer above the Arctic, we need to find out, was it caused by natural processes or is it an anthropogenic chemical effect? To do that, we started already in the early 90s, 1992, with a project that we call the METCH project, which nowadays consists of a dense network of stations in the northern hemispheres. All these red points are stations where we can launch ozone sondes into the stratosphere. These are small instruments that can measure the ozone concentration, and they are carried by big helium-filled balloons up to 30-kilometer altitude, so they can measure the ozone content as a vertical distribution right in the heart of the ozone layer. To now distinguish between natural variability, which is caused by transport, and chemistry, which at that particular season can only be caused by anthropogenic chemistry, we track air masses that have been probed by one individual ozone sonde. We track those and try to probe the same air masses again by another ozone sonde. If we do that, the change in ozone in one individual air mass as it moves over the Arctic inside that polar vortex that Farah has described, we can just single out the chemical effect and distinguish that from the transport effect. And one example is shown here. We have a measurement of an ozone sonde here from our station Nordesund. Then in 5 days, that air mass circled inside that polar vortex and it approached the second station, Sodankule, and we triggered an ozone sonde launch there from Sodankule to measure the same air mass again. This is just a short animation of how that looks like during such a campaign. All these blue dots are air masses that are in our automatic tracking system. So at any time during the winter, when the campaign is still running, we know where these air masses that have been probed previously by one of the ozone sondes are. So these blue dots are air masses that have been probed during the past 10 days by one of the ozone sondes from our network. We also forecast where they will move over the next 2 days, and based on these forecasts, we coordinate the launches from the network such that we probe as many as possible of these air masses twice. Just very briefly want to go through one of these events so that you get a better feeling of how that looks like during winter. This is an ozone sonde launch. During the polar night, it's dark there up in the Arctic. It's dark and cold. Most of these stations are operating under very difficult conditions. So the operators there get up in the middle of the night. If one of these air masses approaches at 2 a.m., then they get up at midnight and prepare the sondes to launch them into the ozone layer, they fill that helium balloon that is this big thing here. It's so dark, so it's a bit blurry, and the ozone sonde is sitting here on that little podest here. So this is the instrument. It's connected with the tether with the balloon, and then that whole thing goes up into the stratosphere and makes a measurement up there. That happened on 30th of January from that station to Dankula, for example. The station is here. And we know for that match event number 512, which I want to show you right here now, that this will approach Goose Bay on the 2nd of February, and the Goose Bay station is this one down there. And now this is 36 hours before the closest approach, and we track that air mass, and 29 hours before it approached Goose Bay, we sent our forecast system, alerted us that that approach would happen, and we sent a launch request to the station for the morning of the 2nd of February. Then things go on. The air mass crosses the Arctic Ocean here. It approaches Canada. 16 hours, 14 hours before the closest approach. 4 hours before the approach, we sent an updated launch time to the station based on the most recent meteorological data. Then 3 hours before the approach, they start the launch preparation of the instrument at the ground. They start filling the balloon 2 hours before the approach, and then 1 hour before the approach, they launch that balloon. And that's an hour before the approach because it takes an hour to get up there. So 1 hour later, the balloon is at 20-kilometer altitude, and it probes the air mass, which is now, if you follow that blue dot, right at the station. So this is one of the events, and we have hundreds of those. And based on that, we can get a very detailed picture of the overall degree of ozone loss in the Arctic stratosphere, and we get the vertical resolution of the ozone loss, not just the column loss. What you have seen before was a model of the ozone loss at one particular layer and measurements of the column loss, and we can now also get the vertical distribution of the ozone loss from measurements. I am in a slightly difficult position here because we are preparing a submission to Nature with the results from this winter. So due to the embargo policy of the journal that you probably all know, I can't give you any details of the results here, but I can certainly say that what we have seen this winter is the largest degree of ozone loss that ever occurred above the northern hemisphere, and that's a robust result. That is when we compare all our measurements with the measurements since the early 90s and also figure in the development of temperatures in the Arctic stratosphere, we can firmly say that this is the largest degree of ozone loss we have ever had in the northern hemisphere. I just briefly want to show you what that means. It has some implications, they are not dramatic. I want to start with saying that. Just to give you a little framework, this is the Antarctic ozone hole, as you probably all know. This is a color scale here, shows you the thickness of the ozone layer. Blue is thin, red is thick. You see the pronounced minimum, which is in the Antarctic deeper than we have seen it this year in the Arctic so far. And that's moving around there above the Antarctic continent. As you can see, it's hardly ever touches populated areas here in Southern America. It sometimes just touches the southern tip of Southern America, but there are not many people living there. In the Arctic, this is an animation of the location of the polar vortex. So those are the air masses that are affected by ozone loss in the Arctic. And this is not from this year. I'll come to this year in a minute. This is from the year 2005. And it's just showing you where these air masses that have been affected by ozone loss move over the northern hemisphere. And as you can see, they move over densely populated areas all the time. They often make excursions to Central Europe. We are sitting in Vienna here. My home institute is in Berlin there. And as you can see, that polar vortex is overhead Germany and Central Europe quite regularly, just because it drifts around so very actively. What does that mean? Now, first I want to show you where the polar vortex this year is, and for that I need to switch to a different program. This is here, 1st of January this year, and it moves over the Arctic here. There's a lot of variability. It tries to split here, it rejoined, but so far it has never really come to Central Europe this winter. We are now in March, but it often is over Canada, in this particular situation here, extending to eastern Russia and to the northernmost parts of China. now it moved in late March over Scandinavia, and it led to increased levels of UV radiation, slightly increased levels of UV radiation in Scandinavia, in Finland, has been measured there by ground stations. And now we are, today it's over central Russia, and it will move east over the next days. It's now moving further east. It will perhaps, that's now a 1 week long forecast, so not really as reliable as a shorter term forecast. It will perhaps touch northern parts of China here, and that is about as far as we can see into the future. But these excursions to other parts of the northern hemisphere, like Central Europe, are frequent, and they can happen all the time. So that may even happen later this year. What would that mean? I again want to compare that with the situation from the 2005 winter, which is the winter where we had the largest ozone loss so far over the northern hemisphere. And this is on a particular day during 2005, the 20th of March, and the remnants of the polar vortex was disintegrating during that time period. We are sitting over Central Europe here, and that led to a UV index of 5 in southern Germany, which is translates to a sunburn time of 20 to 30 minutes in sensitive people. That's not dramatic. It's certainly not more than we usually get in midsummer. So we are well within the range of UV radiation that we sometimes get anyway. But it's quite unusual to get such a high UV index at this season. And therefore, people need to know about that if such situations should occur in the next weeks over Europe here, the sunburn time can be quite a bit shorter than they normally would be at this time of the season. Just to put that into perspective, if we travel to the tropics on holiday trips, UV indexes down there are exceeding 10. They are much, much higher than what we'll ever get here, even if these ozone-depleted air masses should come over our own heads. One last point I want to make here. These are the measurements of our network plotted from all these years and color-coded. These are all the different years. This is the ozone column loss from our measurements. And this is plotted versus what we call VPSC. That's basically a temperature surrogate. It's a measure of coldness. It's an average, winter average volume where the temperature in the stratosphere has been cold enough to allow the formation of polar stratospheric clouds. We would expect large volumes of PSC formation, large ozone losses. So these are the winters up there. This winter right now is not on the map for the reasons I just described. But we have a close relation here. So VPSC is really driving ozone loss. The larger the Z value is, the lower, the more ozone loss we'll get in the Arctic. And this is the long-term evolution of that parameter, VPSC, since the middle 1960s. From radio sound measurements in the Arctic, we know what the temperature have been since the middle 1960s, and it's a continuous up and down. There are these warm winters which don't get any substantial PSC formation, and ozone loss during those winters will always be very small. But there are these cold winters defining the upper envelope of the distribution here, and obviously the cold winters have been getting colder over these past 40 years quite substantially. And this current winter, the blue dot here, it will perhaps move a little further up that line, but not much because PSC activity is still going on, certainly extends this trend. So for the long term, it's clear the CFCs will disappear from the atmosphere. And Gaia has nicely described the tremendous success of the Montreal Protocol in doing that. We are no longer emitting CFCs. At the end of the century, the story will be over. For the next decades, when the CFCs will still be in the atmosphere, the degree of Arctic ozone loss is driven by the temperature. It's basically driven by the long-term evolution of VPSC. We don't really understand what is driving this long-term change in the distribution of VPSC. And as long as we don't understand that, I think it's one of the largest challenges of ozone research right now to understand what is driving this trend and how it will continue into the future, because that will determine how the ozone layer above the Arctic will develop over the next few decades.
Okay, thank you, Marcus. So now I think we open up for questions.
Is this what we're from nature, Is this what we're seeing this year? Actually, an ozone hole, according to the definitions that are in place.
The definitions on ozone holes are not clear. That's one complication. But we are looking all who have presented data today. We are looking at very preliminary data, and the winter is not over yet. The ozone loss is still continuing in the atmosphere. And answering this question is certainly important, but we have to answer that question based on final data, based on thorough analysis, and we'll discuss that question in the scientific literature. I think it's way too early to make a definitive statement about that question right here.
Is there a definition as to
What is an ozone hole, or as to which depletion constitutes an ozone hole?
We had a long discussion among a large group of people over the past few weeks. If I would print that out and show it to you here, it would probably be such a pile of paper. So it's a complicated issue. I think we are agreeing on some basic features of what would constitute an Arctic ozone hole. But again, I think that is something we need to base on data and on robust scientific analysis, and it should be discussed in the scientific literature rather than in a press conference. So I won't comment on that here.
Thanks, Richard Black from the BBC. Is there any correlation, as far as we know, between the unusually warm temperatures that have been seen at ground level over much of the Arctic in the last couple of years and these low temperatures that persist in the stratosphere?
Well, I think what one sees, at least sometimes, that there is like an anti-correlation. That means that if it's cold in the altitude, it's warm on the ground, or vice versa, but maybe not always. I don't know, Marcus, if you have any more.
Well, perhaps we should say the zero-order effect first. The increase of greenhouse gases in the atmosphere shields the higher part of the atmosphere from the thermal radiation that comes from the ground. So the atmosphere is heated from the ground is warm, the atmosphere is cold. The thermal radiation from the ground is absorbed in lower parts of the atmosphere now because greenhouse gases have increased, and that leads to global warming. That is a global warming aspect of the story. The same mechanism means that up there in the stratosphere, temperatures will go down for purely radiative reasons, because the thermal radiation is absorbed at lower levels of the atmosphere and less is reaching that higher levels there. That is a very well-established fact. Models reproduce it, we observe it in data, the stratosphere is cooling. But for the polar temperatures, the situation is much more complicated, because they are not only determined by radiation, but also atmospheric dynamics play a major role in determining the polar temperature in the stratosphere. So there's a lot of mass moved from lower latitudes to higher latitudes during winter. That mass is then sitting on top of the polar column of air, increasing the pressure down there. So it's like when you compress air, it always gets hot. You know that from inflating the tubes of your bicycle, perhaps. If you compress air, it gets hot. That mass compresses the air and it makes the temperature warmer. So the amount of mass we move into the polar regions will also have a strong impact on the temperature evolution in the polar region, and that may respond to climate change as well. And all these processes are not really well understood so far, and therefore I would say it's a major challenge to see whether this long-term change in the distribution of VPSC, which is one aspect of a stratosphere that's getting colder, whether that is really driven by greenhouse gases or not. We can't answer that now, but we certainly need to address it with research projects.
More questions?
I would like to add a comment. So, yes, Jean-Pierre Pomereau. From the models we know, from the climatic models, we have no indication of a further cooling of the solar sphere.
Yeah, that's why I said it's not understood. It's not understood. We see that trend in data, but models are not able to reproduce it so far, and therefore we don't have a good understanding what is driving the trend, and therefore we need to do that research before we can answer the question whether it's driven by greenhouse gases. It's certainly not in conflict with global warming. A cooling stratosphere is not in conflict with global warming. It's important to point that out. Qualitatively, it's in line with what we would expect. The stratosphere should cool in a global warming scenario, but things are more complicated than that.
Holger Kroker, this 40% depletion of ozone, is this evenly distributed over the vortex, or are there local minima?
It's distributed over the vortex, but sometimes locally you can see a 42-45%. And on average, it's 40%.
I think you can actually show it on your figure. Here here on the screen now.
No, you have to.
No, I have
maybe
to press
switch
here, of
again.
course.
So,
No, it's on back to number 1, I think.
number 1.
3. Ah, okay.
Number 3. Okay. There we go. So you see all these individual symbols. They represent stations. And you see the spread is not very big. So they
It's
all measure
2%.
pretty much the same thing, actually. So it's quite evenly distributed.
Because the mixing of the atmosphere is so high.
No.
Right.
There is a large spread at the beginning.
Yeah.
In January, it's when the ozone loss is starting. It's starting on the sun-lit part of the vortex. So with the motion of the vortex totally inhomogeneous inside the vortex in January.
You see here in the beginning, the spread is quite big from one station to another.
Until mid-February, I would say.
And
It's,
then when you get into late February and into March, it really tightens down, you know. See, so
And the vortex becomes homogeneous.
If there are no more questions, then we'll close here, and the journalist will have time to make appointment for an interview.
okay, that's
Yeah,
fine.
Okay, thank you very much.
And the press release.